So talk to your neighbors or move, and then you'll have a neighbor, and then solve this question that is a simpler version of a homework question that I gave at 4:45, and you'll get something a bit more involved, maybe for your homework, but it might include this part. So I generated a family of hash functions, not a very big family, and in this family I am asking if this family is universal or not. And it's not it's not a particularly hard question. So there is a cluster and 3 isolated students. So I don't know if somebody is with us on Zoom or not, or did I send the invitation? Oh, no students? Okay, we have somebody. Alonso, can you hear me?
If you, for every 2 keys and neighbors, if you pick a random hash function, the probability of project is less than 1 over 10. And that's fun.
Alonso, can you hear me? Okay, great. Thanks. And I'm trying to keep an eye on the chat both on Zoom and on the Twitch. But with my ADHD, I don't promise that.
So, in this case, the hashes are the same as the original keys, right? 0 mod 5, 0, right? 1 cs545 is
It says
one.
You don't know the set of k. So k here can be any
I thought-
number.
No, I thought the set of k is 0, 1, 2, 3, 4, 5.
K is the set of
Is it universe the set of keys?
But there is no universal set of keys. There is the universe, and there is a universal family of hash function. The universe is where do I pick keys from.
Yeah.
Okay, so maybe it misunderstood.
We don't know the universe. We just know the set of keys. The set of index.
Oh, I see.
Okay, so I don't know how to arrange group. And we don't have much questions that I planned for today, but let's start with this one. What do you think? Universal?
Yes.
Universal, why? Because what does universal means? For every hash function, take any keys from the universe, the probability that they meet when we are taking the chance that we meet is, or the number of times that we meet when we are checking all the hash functions, the chance that, I'm talking too much. For every k and k prime in the universe, the number of the number of hash function in the family, and remember we have a very small family here, there is only one function, but the number of hash function in the family for which k and k primes collides, age of k equals k, age of k prime, k and k collides. If I'm using this member, if I'm using a different member, this number should be smaller or equal than the number of hash functions in the family divided by m, the number of slots that are working, the possible output. The possible output of this function is, of course, 0, 1, 2, 3, 4, which means that how many of this one function send k and k prime to the same place? 0. Because I take the keys so that they are just age do absolutely nothing. There are no collisions at all. Everybody agrees? There is only one member, and this one member doesn't cause any collisions. And I already warned you that you can find books that will define universal as that the number of such bad hash function is exactly equal to h over m. The definition that I'll use in this course, which is different than the definition of CLRS, is smaller or equal than h over rm. That's essentially what we need from this function. Okay, let's play a bit more. Now I'm making it age I, where this will be ik modulo m, and I goes to 1, 2, 3, 4. Is this family still universal? We mentioning the definition of universality. That's what does it make for a family to be universal? So the part that you missed was that we looked at the function k modulo m, not ik, but just k modulo m. The universe was only these numbers. And now, and we ask when it's just a single function that actually do absolutely nothing, take k into k, will it cause any collisions? And the number is no, which means that this family is universal. Next step, what I just asked before you entered, I finally made it into a family of more than one member, where I'll define age as a set of functions, hi of k. What is hi? of k is I times k, all of it modulo n. And is this family universal?
Excuse this VE or U here is the universal, right? So all of the key must be 0, 1, 2, 3, 4, right?
That's all, yes. And it's an excellent point. So I'm only thinking about keys that are taken from this universe. And this restriction about is this a good universal family or not is with respect to these keys. So I think that some people already figured it out, but I'll let you discuss in the group, and you guys will discuss in your group and take a minute and play with this. The definition of universal is here. A family is universal if for every 2 keys in the universe, ask how many members of the family, how many members of the family, how many different hash functions cause this pair of keys to collide, and the number of functions that cause this key to collide is only h over n. And the way to remember it is just to say, if I pick a random member of the family, I picked a random I, and that would be my family, then is the chance of collision between k and k prime is larger or smaller than the chance of dropping k into a bucket and then dropping k prime into a bucket uniformly. If I get to the same chance, which is 1 over n, then this function is universal. That's the way to remember this formula, at least for me. Okay, now I made it into a family. Alonso, what do you think?
So there will definitely be collisions between different HIs, right? Like if I is 1, then you'll
You can imagine that the university change from, for example, I was equal to,
yeah.
the university will change to 0, 2, 4, 6, 8, and then this.
The question here is, if that's the universe,
It could be the same
right.
basically.
Right.
Don't feel that you're under pressure, Londo. I just picked on you because you mistakenly said that you can hear me, so I picked on you. The question was, I generate several hash functions, namely hi of k is defined as I times k modulo 5. And the universe consists only of these numbers, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4. Is this family universal? Universal is, I remind you, the definition here.
Which will still be the same.
Okay.
HI of k will still be 0, 1, 2, 3, 4. Whatever the key change.
Right.
So maybe it's still universal.
Yeah, I guess the question about universal is like when you're checking if, like in the definition below, are you checking only if there's collisions within a single HI or between different HIs?
No, only for a single HI. I mean, let's follow again the history about why why we need this family instead of a single function. It goes back to question 13 in the homework. Question 13 says, I design my very nice hash function, but I still don't know what is the input. Can I design a hash function that really cause no collision? Answer, absolutely not. I can always generate, if the universe is large enough, I can generate tons of collisions. But then came the next step. Okay, can I then generate a family of hash functions such that no matter what is the input, if I take a hash function at random after the input arrived, but I don't know what's the input yet, but the input is set, just so they didn't tell me about it yet. You already know who are the students that are accepted to the university, but they did not register yet. Can I generate a function that with high probability will be good for this data? And the answer is that yes, if I pick a random function from the family, then for a particular pairs of keys, the probability is 1 over m. It's just like dropping them into m buckets. What's the probability of collision? And if I have a set of n keys, that we usually know, I know what is n, and I usually pick m to be twice n, then the probability of collision of one particular key is half. So the expected number of other keys that will be in the same cell as n is half, meaning that every key has a great chance to be a loner, no collision. Okay, for this question, somebody might commit? Willing to commit? Yes.
It's not universal because when you.
I think it's still universal.
Yeah, I mean, if you have an I. Well, I guess this is my question to start with. Are you randomly picking I, or are you like adding them?
The hash function says, the definition of universality says, I'm counting how many hash functions there are in the family, how many n members that are bad for this pair of keys. I fix my pair of keys, and I'm asking how many hash functions are there that cause the collision between this particular pair of keys. And to be universal, the requirement is that for any pair of keys from the universe, any pair of keys, the number of functions that cause the collision should be small. Most functions should send k and k prime to different locations, independent of what is k and what is k prime, as long as it's in the universe. Meaning that to count it, I need to ask, I don't know what is k and k prime. Of course, I do know that they are different. Otherwise, yes. And I'll ask for age 1, that is 1 times k. Will there be a collision? For k2, will there be a collision? Yada yada, up to not too many cases. And if yes, then count it.
I think it's still universal.
It's still universal because, and we need here a little lemma.
At least for me,
Because
for this case, we know that both I and k is still smaller than 5, so multiply of them, multiply is still the same. It's as in there are no collision.
excellent point, but how do I know that IK mod 5 is different than IK prime mod 5? There is one important sentence that you must say here. And you can say I checked all the cases because 5 is not a large number, but
You can split it into I mod 5 times k mod 5, and you know that k mod 5 is not the same as k prime mod 5.
but the modulo might cause issues. I mean, you're almost right, but I think that I can generate I think that I can generate by input if you'll allow me to replace the 5 by 8. We'll have to think for a moment if I'm right, but I think that I can generate bad inputs if it's different k and k primes that will end up at the same place.
So k minus k naught is less than 5, and 5 is prime, so.
And prime is 5. Exactly. Prime is 5. What we mentioned is that if I pick k, if I pick I is the same and I run through all the keys, I'm getting different numbers. I'm generating a different permutation. Every I will generate a different permutation. Permutation means you're not missing anybody and you're not double hitting anybody, which is not true if it's not a prime. Which doesn't mean that not a prime is necessarily making it a terrible function, but at least you are not enjoying the theoretical background that the dot product will work smoothless in your case. And last modification. Same question, but the universe is a bit larger. Is the family universal or By the way, for the record, if it was too fast, before adding the files, the family was universal, but we needed this lemma from last meeting that what M being prime buys us. Okay, and in this case?
Universal, because every time we get I as I, then that mod 5 is always 0, whatever the case.
There is a pair of keys in the universe, in the new universe, extended universe, for which H1 caused the collision, H2 caused the collision, H3 caused the collision. 0 and 5 will never, doesn't care what I'm doing to them later. They'll cause the collision. They'll always collide. Okay, so some version of it will be in the homework, of course, but now at least I wanted to reinforce the notion of universality. One other small thing that I want to make sure that everybody understand is that if I have two numbers A and B, then A plus B mod M equals A mod M plus B mod M, almost true. A plus B mod M is like, I can do, if I have to compute the sum of two numbers and they are too large when I sum them up, they are too large to my taste, I can take the first one, compute the modulo, I can take the second one, compute the modulo, and add these modulos, and I'll get almost always the same thing. Possibly I'll get something that is larger than M. Then for all of it, I still need to do mod M at the end, just to make sure, because it could be somewhere between M and 2M. Okay, and the same way when I multiply them, M times B equals same thing, also mod M. Why is this useful? Because sometimes some people suggested different hash function than the dot product, but involve generating a very large number. Numbers that is, if in question 14 you had inputs which were strings of 50 characters, then it can generate the strings with 100 many characters. So it's not convenient to do modulo on it directly. Instead, you're looking at the numbers as it grows. The same goes for the dot product, by the way. You look at the number as it grows, and once it starts to be larger than M, just compute the modulo. Since you're doing modulo M anyhow at the end, then it doesn't help you to do modulo M as you are doing the calculation. Again, I'm looking at sequence of values in the case of the dot product. I'm looking at A1, K1 plus A2, K2 plus A3, K3. I'm referring to the notation of the dot product. Plus dot, 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 dot. At some point when I'm looking at the sum, it starts to be, some moment it starts to be larger than what I can fit into 64 bits word, or long float or long int. What do? Anyhow, I am planning to do modulo M at the end after I compute the sum. But once this partial sum becomes larger than M, just compute, replace it by mod M immediately. And keep on going, of course. Okay, let's finish perfect hashing if there are no other questions. We discovered that if we are allocating for the hash table, if we allocate for the hash table huge amount of memory, like quadratic memory, I should have highlighted it, M, which is n squared, then with high probability, I don't have collisions at all. That is, there is a probability half that I don't have any collisions at all. And this probability of half telling you that here is an algorithm that actually finds such a hash table. But that's how we are moving from probability to expectation. I tried one function, generating it by picking a member from a universal family. There is probability half of no collision. I check it out. If this function works, great. If this function doesn't work, I'll just try another one. So this algorithm might never stop, but it's not very likely. But on average, it will stop after 2 iterations. It just is asking, toss a coin, a fair coin, and stops the moment that you have face. So it might be tail, it might be tail, face, or tail, tail, face, or tail, 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 face, and so on, but eventually a face will appear. One might hope. Okay, so how does a perfect hash function works? Hash function that doesn't have any collisions has linear memory. No collisions means that find operation takes constant time. Insert I'm not talking about because I assume that I know what is the set of students. I'm not trying to address insert at all. I'm just trying to generate it so I can have a nice way to do lookup table. Is somebody in the university or not? So what are we doing? To start with, I'll pick a hash function which look at the set of keys, and this hash function doesn't assume quadratic memory. It assumes n memory where the main hash function, I'm not sure that it appears in the slides, but double check here. So my first hash function that I'm building, the first level of the table is, will assume linear memory. That is, I'm treating it as if it's any normal hash function for data structure application, at which I pick m to be larger than 2 times n. I have some guesstimate about how many students are going to appear. And m is prime. Okay, and that's how I build my original hash function. And now I'm checking, of course, what is, we'll see a bit later, I'll check what is sigma over all the ij of cxy of this hash function h. What is this notation? I'll remind you from last time. cxy is 1 if age of x equals age of y, and 0 otherwise. Okay, but if this hash function does what it expected to do, what we proved that most hash functions are doing, is that we proved that the expected number of the sum sigma of xy in k, xy in k of cxy of h is what? it is about half for each one of the elements, so it is n over n. That's what a hash function is expected to do, to generate a probability of half for each one of the keys. And let's remind everybody what the general problems that we are solving with a perfect hash function. I discussed it last meeting, but I'll tell you once again. Somebody gave you a set K of keys. You don't have any control about who are these keys, K1, K2, all the way up to Kn. N is a number of keys. But you do know what are these keys. You know what are these keys, and I'm not going to change them dynamically to insert any more keys. And I'm trying to build a hash function. It's going to be actually a complicated hash function. It's hash algorithm, if you want to call it this way, that will make sure that for every key that you give me, I can in constant time say this key appears in the set K, and that the details of the student associated with this, or this key that you gave me is not in the set K. And I want to do it in constant time. Remember, normal hash function, just do it in expected time, not worst case. And now I insist on worst case. Okay, so remember, for a general hash function, the number of collisions, what does this number tell you? You decided about a hash function, how many collisions are there, how many pairs you have that collide. And now I take this hash function, and I think about it as, here is my table that I create for the original hash function H, and a few keys are mapped into slot 1. In this case, K14 and 27 are mapped into slot 1. Into slot 2, nobody is mapped. Into slot 4, 26, and into slot 6, I have 40, 37, and 22. And what's the big plan? When I'll store a different hash functions and different hash table for each one of these sets. I have possibly n different sets. If I'm lucky, each one is in constant size, but more realistically, I'll have sets with a few students, I'll have sets with no students, some keys or no keys. Okay, and I'll use age to help me access this table and one particular slot of this table, but then I'll have one more hash table to check. Yes, sir.
I'm probably missing something, but what is the A column represent? Like, where's the number 31 come from?
At this point, I stored the slides of Charles.
Okay.
I just only need to assume it refers to a previous part where he was building this family specifically. So, yeah,
So there's
I
only
couldn't.
one hash.
But for now, I'm going to build various hashes. So I have
Right.
some educated guesses about what these numbers could be.
Okay.
But in my lectures, they don't necessarily mean anything.
Okay.
The first column does tell you something. What does it tell you? So I could have arranged all the elements here. First, I need to give them a name. S1 is a set of keys that are in the first, that are mapped into slot 1. S6 is a set of keys that are mapped into slot 6. Next, I am going to concentrate only on the keys that are in S6. Si are all the x such that age of x, the one that we're using, is send it into slot I. And in the philosophical level, we want to understand that being a good hash function, even if we picked it from universal family and we did our homework properly, being a good hash function means that there are very few collisions, both when I aggregate it among all the keys, And every key will have very few collisions with other keys. But it definitely does not say no collisions at all for all the keys. It's way too unlikely. If I want to guarantee no collisions at all with high probability, I need to go to M that is quadratic in size. But here comes the cool part. So everybody understand what are the different SIs? If I would think about chain hashing, I would just put a linked list after from each entry of the hash table. But to search inside this linked list, it's not a constant time necessarily. There will be one of the items that have a lot of keys. It's unlikely that they will all be of constant size. Instead, what I do, I look at the first, I look at how many keys there are that are going to S1, and I remember the previous slide that told me if you're taking a hash table that is quadratic in size, but quadratic in what? Quadratic in the number of keys that are mapped to this slot. It's not quadratic in the number of all the keys. It's quadratic in the number of keys that are mapped into this slot only. That's why quadratic will mean I have 2 keys, allocate 4 slots. I have 3 keys, allocate 3 square, 9 slots for the table. And now for this table, generate its own hash function. Of course, why it's not from the family? Because the M that you're using here is just the number of keys squared, the size of the table. It's different M's at each iteration, for each table. But what does the previous slide told us? That once I reach this table of quadratic size, I'll just need a in this table with high probabilities there are no collisions. And I'll try with the first hash function. So I know what should be the size of the table. I'll pick one family for my one member for my family. If it works, great. If it doesn't work, that is, there are some collisions. Pick another one because you have probability half that it worked first for the first slot. After, on average, 2 twice, you hit the right hash function that refers to this set. And then you're moving to the next set, moving to the next set, and so on. So right now I don't have any collisions. Remember the algorithm. How do I find the key? I first find the slot, like in chain hashing, but as opposed to chain hashing, I have another hash function that maps me into this area. Now comes the next part that asks, hey, why did you need all this headache? You had, if you want no collisions, you had already a solution that used n square memory, but give you with high probability no collisions at all. How do you know that now with your new multi-level architecture, there is still no collisions? And the answer is, let's ask what is the average size when I'll sum up the size of S1 plus S2 plus S3 and plus S4. If I don't believe that the camera sees. S1 plus S2 plus S3 plus dot 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 Sn, if I have one. All these numbers, the size, the set of keys that are mapped to slot 1, the set of keys that are mapped to slot 2, all the way to the set of keys that are mapped to slot n. What is this number? This is just n. That's how many keys I have. I just partitioned them. But that's not my question. My question was, I looked at the set S1 of keys, and I generated a table of size of the set square. Same for S2, same for S3, same for Sn. So what can I say about this summation? But let's think about this square. What does it mean? Let's look at S1, and let's assume which set can we use? Let's look at S6 in this example. S6, that consists of 40 37, and 22. And we are allocating a table of quadratic of 3, that is of 9. But then let's put this, if you wish, this table that will say that for 40 and for 40 and 30 and 37, they collide by the first function. For 37 and 22, there is a collision between every such pair. But I just created a table, look very smartly, I'm missing something, 40, 37, and 92. I just created this table that is quadratic in size. I just considered all the pairs. I just count differently what is S1 or S6 that are counted over here. It's just this table of all these guys. Every pair that is summed up. And every two SI and SJ that are every two keys that one comes from SI, one comes from SJ. What will be the CXYH for two keys? One comes from this set and one comes from this set. Well, our hash function sends them to different locations. So C will be 0 in their case. This indicator will be 0. They are not sent into the same case. So all I'm trying to convince you is that this summation that you see over here, the sum of C of xy, on or off, collide or not collide, with respect to this function h, is order n over m. It's actually when no, it's actually it's not n over it. For one, it was n over n. Sorry, for n of them, it was n square over m. And so it's n square over m, which so that comes directly from the theorem that we had last time, which just means that the expected sum of what? Ni, the size of the set Si, squared, the size of the table. This big thing is just the size of the table of quadratic size. Sum it up for all the different i's, all the different sets, you're still in linear world. So the memory is still linear. Okay, again, what was the catch here? The catch was that, sure, I'm using quadratic size tables, but it's quadratic size for sets that are very small. The first hash function helps me to break my input into small sets. And for a small set, if I use quadratic space, it's not the same as first aggregate everybody and then do quadratic set of the large set. Okay.
So just to make sure I understand what you're saying, so the expectation of the size of any of the sets that you're hashing into is constant, so the total storage is constant?
That's a bit too much to expect with linear part. I cannot argue that with high probability it will be a constant number of elements per each slot.
Right.
That's too good to be true. I'll have
The
slots that have
expectation
about
over
log
all
n. Log n is roughly what you'll expect as a maximum slot if everything is random.
Okay.
No way, yeah. So you'll have larger component and smaller component, but still when you're taking the squares of all these numbers, it will not be n, it will be order n.
Right.
But essentially what's written here. And since m is about 2n, then that brings us to this number. Okay, and to prove that this is n over m, what we put was just immediately from the definition. We just counted for all the hash functions. For one particular x, look at one particular y. Ask how many hash functions are colliding, which would be 1 over m of the total hash function. So now if I look at one particular x, all the different y's, it would be 1 over m, 1 over m, 1 over m, and I have it n times, and m is twice n. So that was 1 over m plus 1 over m plus 1 over m. Remember, I'm keeping x the same, but I'm iterating over all the y's in the set. That was 1 over m, that is summarized n minus 1 times, give us n minus 1 over m, which is half. M is twice the size of a. So for one particular x, that was a number. And now if I repeat the same exercise for every x might be any one of the sets, but ask for any other set. Are they colliding? Then I'm taking this number and just multiply it by. Good. Let's move on. I also thought of showing you more application of hashing for other things, and I think that Rabin algorithm for string matching, I'll also teach it. It's ingenious, fantastic algorithm that find a string in substring, which you need either if you are looking for text, or if you are trying to find a virus in a program, and this virus is naively didn't morph enough so you can see it. Why does it look so small? So something about this slide is. Okay, I'll edit this slide later. Yeah. How do we resolve collision? A lot of you have covered most of what I'm talking about in previous courses. I'll go as fast as you want. Collisions, unless you are using perfect hash function, which is not good for dynamic data, it assumes that I know the data ahead of time. So no perfect hash function. So collisions happens. Hopefully not a lot of them. How am I getting rid of collisions? Chain hashing. Chain hashing, every slot contains a linked list. What can I say about this chain hashing as a way to solve collisions? Insertion can be done in order 1, but I can always insert a new key in the beginning of the linked list. No randomization here. Search takes the length of this list. If I want to make sure that the worst case running time is better than n, I can replace it with a tree or a skip list or another hash table or whatever I want as a secondary data structure and do various tricks. That's pretty much summarizing good things that I can tell about chain hashing. Otherwise, I can only say bad things. It requires dynamic memory allocation, and dynamic memory allocation is bad to multiple things. It's bad because it takes a lot of time. You're asking the operating system, please give me a new cell somewhere, and this new cell might be far, far away from the rest of your array and the rest of your keys, where it is allocated in memory. You need to run garbage collection. It's results several vulnerabilities in terms of the penetrating of security of the code. If you're running optimizer on your code, optimizer that comes before the compiler, it is much less efficient. GPUs really don't like linked list. Many bad things. It's hard to verify this program, putting it on different virtual machines. If you can stay away from dynamic memory allocation, your program, for whichever application your program will run faster and is more likely to crash for various reasons. Coco hashing, we'll discuss later. Where is this name is coming from? It comes from a bird that lay its eggs in the nest of other birds. So we'll see how this idea is taken to create to resolve collisions in the hashing and even provide an order 1 search time for the memory. So it's as good as perfect as far as search time. Insert is not necessarily constant, but is most likely to be a constant as well. Finally, and the most popular is open addressing. And open addressing is a general technique at which we are only using one large array that stores everything, where the same key k might appear is mapped to some index age of k, but then depending on the availability, it might be mapped or might store in different locations, depending on availability. An example is coming very soon. So if I'm using open addressing, and terminology here is confusing, I'll tell you in a moment why, but this is just the definition of an open addressing. And then we'll have double hashing, that is one special case of open addressing. So a hash, now my hash function should contain two parameters. One is the key itself. The key can be, and how does it manipulate on the key? Dot product, multiplication, and of the previous hash function. But it also have I that specify my trial number. Trial 0, trial 1, trial 2, trial 3, and so on. First trial, to confuse everybody, the first trial will be trial 0. Okay. So, one simple example would be age of k key, and I would be just k plus I modulo m. That would be called linear poly. Another example, age of ki would be k plus I times another hash function modulo n. That's double addressing. I'm using two hash functions. One that tells me what is my first location that I'm looking for, and the second one that tells me by how much to jump. And there will be also age of k equal k plus I squared modulo m that tries to solve some of the problems that the first hash function that the linear hashing solves. And I think that I skipped over something that I did want to tell you. Yeah, that's okay. So how do we insert a key in each one of the operations? We are computing our first trial. Look at the hash table at index what? Age of k, comma 0, because it's the first trial. If it's empty, that's where we insert k. Otherwise, try age of k in your second trial, okay, I equal 1. Keep on trying until you either find an empty slot or you're getting to the case, to your nth trial, m is the size of the table as usual. And at this point, you give up. Okay, so we'll have a sequence of trial, quick example. I assume that at best I'm reminding people stuff that they saw earlier. Very simple hash function, k plus I modulo m, modulo 8. Cannot be much simpler than this. Insert of 12 into a table with 8 slots. 12 modulo 8 is 4. 4 is empty. Insert 12 over here. Insert 15. Age of 15, comma 0 is 15 modulo 8 is 7. Here is where 15 is going to sit. Insert 20. Age of 20, comma 0 is 4. I'm going to sell 4. And oops, there is somebody living there already. So I'll try my second trial with I equal 1. Second trial, age of 20, comma 1 is what? 20 plus 1 modulo 8. Give me 5. So that's where 20 is going to appear. 23, age of 23, comma There is 7, there is a collision because somebody lives over here. So age of 23,1 is just the next one, because it's an example of linear probing just the next cell, is 3, and that's where I'm inserting. Okay, inserting 28, yada yada, inserting 28, and now I did the unheardable, but I figure out that shift arrow moved me to the next one. Okay, I jumped over a few cases, but we'll survive. Okay, so how do I do a search? Doing a search, I'm just trying to follow the same trials, the same set of trials that I did while I do the insert. Right. What would be, I'm looking now for 28. Where will I try to insert 28? Let's compute what is 28, 0. First trial. Modulo 8, take me to cell 4. Somebody is living in this cell, but it's not 28. So possibly I try to insert 28, but somebody was living here. So what would be the next cell that I'll try? Next cell that I'll try to insert, but would be the next cell. So now when I'm searching, I'm just following the same path. I'll try to, if I insert it, I'll try to insert it over here. Not 28 yet. Finally, I found 28, and I'm happy. Right? And well, let's search 16. 16 modulo 8 takes us to cell 0. I did not find 28. Trying the next cell next cell is empty, so the logic is if 28 would have been inserted at some point, it would try to be inserted over here, and if that's busy, try to insert in the next part. Since I got to an empty cell right now, I conclude that this empty cell indicates that 16 is not in the table. So hitting an empty cell is our indication that it's not in the table. Okay, so you search the same probing policy once as before. You are stopping it if you tried n attempts and you didn't find what you are looking for. And now I think that you all know what I'm going to do. I deleted one of the keys. I deleted 20. 20 doesn't exist anymore. And yeah, I did something bad to the slide with the animation. And now I'm trying to find 28. Find 28. What will be your first trial when you search 28? 28 modulo 8 will be 4, but 28 is not here. Next cell, empty. My search stops and declares that 28 is not in the table. Ignoring the fact that had I continued the search, the reason that I didn't find 28 here is because there was somebody that was living here. But that's the reason that it's empty. Somebody was living here that caused me to put 28 in a different location. So what's the problem? That I need to do something else when I'm in. Yeah, this animation is terrible. Now you see it. Let's search uses the same probability now, and we look for 28. We didn't do it. What's the solution? You all know it. Once you're deleting somebody, put a gravestone on this place. Somebody used to live here, but not anymore. I don't care who it is. But if you're doing a search and you hit a gravestone, keep on trying. If you are doing an insert and hit a gravestone, a dummy, a flag, then realize that this cell is empty and you can place somebody inside. Okay. So that's one modification, one complication that we are suffering because of open hashing. From time to time, do the maintenance. I'll talk more about the maintenance. Really important to do maintenance, namely do a rehashing. which is take all the keys out and now insert them, possibly without, of course, the flags and the dummies. And that's also a good time to decide that your table is too occupied, so you need to rehash. Lina?
Sorry. I have a quick question. Is that still we are only using one big table for the whole hash?
Yeah.
Yeah, I think then the storage would be like much larger than compared to the previous one where we had
No, because it's still of linear size. The size of this table is prime or not prime, about 2n, so twice the number of keys. I'll convince you in 3 minutes that it makes sense. It's still a good idea. Okay, linear probing, the infamous linear probing. So what is linear probing? H of ki is nothing but use one hash function. The prime here has nothing to do with derivative. It's just a different hash function. Of course, I'm a big fan of dot product, use a dot product, whatever fits your keys over here. And if you need more trials, they will just come straight after your original trial, just continue linearly. And of course, the modulo n will make it cycle. Right? If you get to the end of the table, just go back to the beginning. Every student that I ever had knows to quote that from different courses that it caused a lot of cluster. Right? Because if you have some cluster here, linear probing has this terrible phenomenon that if I created, here is my table, inside my table, this part is occupied. This is already occupied, maybe I have more clusters, and now I'm trying to insert any key that hits this cluster. Anywhere that I'm trying to insert and I hit any key of this cluster, what will happen to my cluster? It necessarily, the new key will just be at the end of the cluster. Other strategies, like the quadratic probing, will try to say the cluster, some of the keys will jump to different location, and how much do I jump or where do I try my next attempt varies between different keys. But linear probing will say, I don't care what the key is, just try the next one, the next one, the next one. So theoretically, it's quite inferior method. Practically, well, we theoreticians don't like that there is a practice world, but unfortunately we cannot avoid it. That in practice it works extremely well, and I mean it's depending on the application, but in general, when we are talking about our computers, there is a hierarchy of memory. To start with, it starts from just main memory and SSD, or memory and hard drive, and if you have an array, and this array is really large, really large, how does your computer handle it? It takes pieces of the array and put it on the hard drive. Or in slower memory, if you have the whole hierarchy. Some pieces of the memory are not as available as other pieces. Now, you try to do find of key at index I, so you accessed some address over here. It's so quite likely that this is in the top of the hierarchy, the fastest cache that you can have, which suggests, because of locality, that the next cells are also waiting for you in the fastest memory as well. The whole block of memory is moving. Usually you're not moving between the memories, just individual bytes, but you're trying to move big chunks of contiguous memory. So because of locality, if you access this cell, then it will probably be very fast to access the next and the next and the next. Make sense? So that's why, despite all the bad mouthing that theoreticians will do to linear probing, it's in practice, depending on application, depending on your memory, can work quite well. Double hashing will say your hash function consists of two hash functions. One is your first trial, and second one fixed by the key, but different between different keys, says by how much do I jump. Think about a frog that will try. Frog will have multiple attempts. It will first try age 1 of k, and if that's occupied, it jumps by some amount, and this amount of jump is age 2 of k. But if this cell is occupied, then I'll make the very same jump once again. Same jump, same jump, same jump. And you naively might ask, or I naively might ask, don't we get the same problem of clustering that we had beforehand with the linear probing? Don't we have the same problem of clustering, just that now instead of the cluster being smooshed together, the cluster goes by different jumps? And the answer is that there is a good chance that no, you don't get the same type of clusters. Why? Because a new key might hit the table at a different location between the jumps. And more importantly, that even if two keys are meeting each other, age 1 of key and age 1 of key prime, both send you into the same location, then good chance that the next jump will take them to different locations, because age 2 of k and age 2 of k prime will be different. That is, age 2 of k took us to here, while age 2 of k prime will send us to a different path. I'm not going to repeat if I inserted k and then I inserted k prime, then even if they met once, they separate in the continuous path. While in linear probing, they are following exactly the same trail of each other. Once two keys met, they'll keep meeting in all their future paths. So you are breaking the clusters at some point. There are a few obvious issues with H2, which are, what do you need to be careful about H2? And there is one obvious thing that you want to make sure that H2 avoids. But once you choose H2, it doesn't mean that you are using it literally exactly. It can be a little algorithm, little, C function, if, then, else, other. So what would you suggest? I start to write the pseudocode of H2. What would you suggest? I'm not talking about H1 at all, just about H2. I can do H2 of k would be, let's say, R equals AK mod 30. And I'll return R. Unconditionally return R. I mean, before we are getting to the question about prime or not prime, there is an obvious bug that you want to avoid.
So you want to make sure that the total hash can iterate through every location in the table without a collision.
What?
So, I mean, you have it up there that H2 must be relatively prime to M.
Yes, but there is a little stupid case that they don't mention.
Yeah, I don't know.
If I use this one,
You have to make sure R is not equal to 0.
no, it's not 0. Like, if H2 is 0, then I times 0 doesn't make much progress. So yes, of course, we want to make it prime to 0. We also want to make sure that it's not a divisor of M. Why? Because if it is a divisor of M, let's think about it. Here is my table, 0, 1, 2, 3, 4, 5, 6 numbers. Let's say that m is not a prime, m equals 6. Let's say that I pick all the keys that I'm going to pick next will satisfy that h2 of each one of the keys that I'm going to pick will be 3. Why is this a bad thing? Because now let's insert somebody. I don't do the math. I will do the math. I'll just add 6 at each time. So let's assume that I insert 9. So my original hash function would be k mod 6. That is my hash function. 9 mod 6 takes me into 3. That's where I'll store it. Now I'll insert 12 mod 6, put 12 over here, and now I'll insert 15. I'll try to access cell 3, occupied, so it adds h2. And in the case I equal 1, add h2, add 3. So now I'm in 6 mod, I'm in 12 mod 6, take me into 12, occupied, adding h2 once again, case of I equal 2. So I'm checking 3 cells after 0, takes me to here. Right? And you see the problem. The table is mostly empty, but still I cannot insert one more key. Why? Because h2 was picking stupidly enough, so it is a divisor of the size of the table. But this phenomenon that I'm going to show you, that I'm just alternating between two cells, no matter what is I, if h2 of k returns 3, then you're just going to probe a subset of the cells of the table. After a few probes, you will end where you started. Make sense? So it could be that you are trying to insert a key, and the insert performs m iterations, says the table, as much as I know, is completely full, while the table is almost completely empty, just because h2 divides m. But there is a simple remedy. Primes don't have a lot of numbers that divides it. I expect you all to understand what's the problem exactly. If h2 does divide m, what is this cycling phenomenon that I'm trying to explain? And let's try to analyze the running time. Should we, or yeah, let's wait. Well, for a change, I will not hold you over time. For a change. So I can speak for a long time about why I'm not planning to hold you for over time. Yeah, thanks everybody, and yeah, and homework 4 is coming up.